So if we add an electron to a neutral atom, this is called electron affinity. This is the energy change. And it's different. It's the opposite, in essence, of ionization energy. So look at your periodic table. Think about something that has very, very high ionization energy and stick your finger on it. Okay. What do you have your finger on there, Ms. Fisher? Neon? Okay. What do you have your finger on there, Grant?
Fluorine.
Fluorine. Okay, good. I like that. We're going to take fluorine. We're going to talk about fluorine. So, fluorine has got the second highest ionization energy in its period, right? Only higher in its period would be the noble gas, neon. So you had a nice little pair there, neon and fluorine. Do you think we could get fluorine to take an electron? Yeah. Because guess what? If fluorine takes one electron, guess who it's just like? Neon. Ooh, 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 I want to be like neon. I want to be like a noble gas. I want to be a noble gas. Everybody wants to be a noble gas. So if a halogen can take one electron, it will be just like a noble gas. It'll be so cool. You're going to dress up as a noble gas?
Yeah.
I think I just figured out my daughter's Halloween costume.
Noble gas.
So, yeah. I'm not sure how I'm going to pull it off yet, but I'll manage.
Well, what you do is.
So, anyway,
What? I was going to tell you.
we're gonna, nope.
Why?
We're gonna,
It might be the best idea ever.
Daniel, recording for YouTube. Okay. If energy is released, this statement's going to have to be illustrated. When an atom accepts an electron, then the electron affinity is considered to be negative. So let's take fluorine, and let's say that fluorine, all by itself, has this much potential energy. So fluorine potential energy. Okay? Think about a rock balanced on the top of a cliff. Is that stable? Not particularly. So things that have very high potential energy tend to be a little bit unstable. You know, the rock that's on the edge of the high cliff. So fluorine is kind of unstable by itself. When fluorine takes an electron, its energy level actually drops. So the fluorine ion has got lower potential energy than the fluorine atom. So look at that difference in energy. Where does that energy go? You can't lose energy. It's released out into the world. It goes poof, out into the world. So as long as energy is released when an atom accepts an electron, we not only consider the electron affinity to be negative, but if energy is released, that means that atom is more stable once it's taken on an electron. We've taken that rock that's perched on the hillside and we've brought it down and set it on the ground. It's more stable, it's got lower potential energy. Now, if the opposite is true, and let's imagine something like sodium. So here's sodium, neutral atom of sodium. Sodium has got a really pretty low ionization energy. Could we get sodium to take an additional electron? We'd have to really force it. So if we forced an extra electron on sodium, it's less stable. We've taken that rock that's on the cliff and we've pushed it up to an even higher cliff. We've rolled it up the hill. So let's imagine, we're going to draw a little cartoon here. You've got this cliff this rock, and a second cliff. If you want to get this rock, and there's the ground. If you want to get this rock up to here, you're going to have to push it. So here's you pushing that boulder up a cliff.
Nice drawing.
Is that a stable position? No. What's going to happen the second you let go of the boulder? You're going to be smashed flat like a little pancake. Ew. It's totally not stable. It's never going to be stable. You're never going to get that rock to just sit there. That's sodium plus an electron. That's something with a positive electron affinity. Those things are never stable. It's never going to keep that electron. The very second you let go, it's gone. So this is sodium plus an electron, is that. Now if we have this there, and we go ahead and drop it to there, is that stable? Yeah. That's very stable. That rock at the bottom of the cliff is not going anywhere. That's fluorine plus an electron. Okay? This is fluorine plus an electron. Fluorine would love to take on an electron. That rock would love to roll off that cliff. Once it gets the electron, it's perfectly stable. It will keep the electron. Unlike sodium plus an electron, that's going to spit it right back out the second you let go. I do like our little person pushing the rock. Okay. So, if we look at our periodic table again, the halogens are real happy to take an electron. So as we go across a period, starting from, so let's go across from sodium to argon. Sodium has got a positive electron affinity. It's unstable with electrons. That electron affinity gets more and more and more and more and more negative as we go all the way over to the halogens. The halogens have the most negative electron affinity on the whole periodic table. They are all boulders sitting on the edge of cliffs that just want to roll to the ground and sit there with an electron. Okay? Are the boulders confusing?
What has more
The halogens have the most negative electron affinity. So it gets more negative as we go this direction, as we go from group 1 to group 17. Okay, so now let's talk a little bit about ionic radii. Two terms to remember. Positive ions are cations. They're little cat ions. I don't care how you feel about cats. Petting your cat is a positive experience. That's a mnemonic for remembering that cat ions are positive ions. Anions are negative ions. Anti, negative. Easy, right? So when we form a cat ion, the atomic radii decreases. So let's draw that with lithium. So here's lithium. It's got 3 protons, 1 electron in that outer shell, 2 electrons on the first shell. When we form lithium 1+, the radius decreases. 2 reasons. So, jot them down. What do you think? One is real obvious from that drawing, and it's not the case for all of these things. Why would that decrease the radius? So as you think about that, I'm going to draw fluorine for you. So fluorine forms an anion, a negative ion. And we have fluorine with what? 9 protons, 1, 2 electrons, 1, 2, 3, 4, 5, 6, 7. Okay. When we form fluorine 1 plus, we still have 9 protons, and we now have 8 electrons. My drawing is terrible, but that's okay. And it gets fluffier. So why, when we form a positive ion, does the atomic radius decrease? When we form a negative ion, it increases. How can you explain both of those things in one fell swoop? Jot something down. And I'm going to turn off the video camera, and I'm going to have you guys discuss with one another. Okay, so think about it.